Picture a time, billions of years ago, when the moon wasn't the barren, cratered landscape we see today. Instead, it was a blazing world, covered by an ocean of molten rock. This isn't science fiction. It's a theory that's becoming increasingly supported by new data from India's Chandrayaan-3 mission. On August 23, 2023, the Indian Space Research Organization, or ISRO, made history when its Chandrayaan-3 mission successfully landed near the moon's south pole. This was the furthest south any spacecraft had ever touched down on the lunar surface. But this wasn't just about setting records. The mission had a critical scientific purpose: to explore one of the moon's least understood regions, and to gather data that could help us unlock the mysteries of its ancient past. So, why the South Pole? The moon's South Pole holds particular interest for scientists because it's home to some of the most ancient and well-preserved geological features on the lunar surface. Unlike the areas explored by the Apollo missions, which landed closer to the moon's equator, the South Pole has regions that are permanently shadowed, meaning they've been untouched by sunlight for billions of years. This makes them perfect time capsules for understanding the moon's, and by extension, the Earth's earliest history. Once Chandrayaan-3's lander, Vikram, touched down, it deployed a rover named Pragyan. This small but powerful rover set out to examine the surrounding lunar soil, or regolith. What it found was extraordinary. The soil in the region around the landing site was composed primarily of a type of rock known as Faroan anorthosite. This rock, which is rich in calcium and aluminum, is believed eventually forming the moon's outer crust. This idea of a lunar magma ocean has been around for decades, ever since scientists analyzed the samples brought back by the Apollo missions. But Chandrayaan-3's findings bring new evidence to the table, particularly from a region of the moon that hadn't been explored before. What's fascinating is that the chemical composition of the regolith, measured by Pragyan, closely resembles the soil samples collected by the Apollo 16 mission in 1972. The lunar highlands, far from the South Pole, yet the similarities in composition suggest that this ancient magma ocean once covered the entire moon. However, the Chandrayaan-3 findings don't just stop at supporting the lunar magma ocean theory. They also challenge it in intriguing ways. For example, the rover found higher than expected levels of magnesium in the lunar soil. This suggests that the region's crust may be a mix of the original Faroan anorthosite and more magnesium-rich materials from deeper within the moon. This could mean that the lunar crust isn't as uniform as the traditional magma ocean model suggests. Now let's talk about the South Pole-Aitken Basin. This massive impact crater is one of the largest in the solar system, stretching over 2,500 kilometers in diameter. It's thought to have been created by a colossal impact early in the moon's history, an event that would have thrown up vast amounts of material from the moon's interior, scattering it across the surface. Some of this material may have ended up at the Chandrayaan-3 landing site, which could explain the unusual chemical signature detected by the rover. But why is this important? By understanding the composition of the lunar surface at the South Pole, scientists can gain valuable insights into the moon's overall geological history. This in turn helps us refine our models of how the moon formed and evolved over time. And it's not just about the moon. Since the moon and Earth share a common origin, this research could also shed light on the early history of our own planet. One of the most widely accepted theories for the moon's formation is the giant impact hypothesis. According to this theory, the moon was formed after a Mars-sized planet collided with the early Earth, ejecting a huge amount of debris into space. This debris eventually coalesced to form the moon. The idea of a lunar magma ocean fits neatly into this model because the energy from such a massive impact would have been enough to melt much of the material that formed the moon. As the moon cooled, its surface would have solidified first, forming a thin crust, while the deeper layers remained molten for a longer period. Over time, the remaining magma would have cooled and crystallized, forming the different layers of the lunar interior that we see today. But it's the topmost layer, the crust, that holds the key to understanding the moon's, and by extension, the Earth's earliest history. Chandrayaan-3's findings are particularly exciting because they provide a ground truth for the data collected by previous missions. For example, India's earlier lunar missions, Chandrayaan-1 and Chandrayaan-2, Both used remote sensing instruments to measure the chemical composition of the moon's surface from orbit. These orbital measurements suggested that the surface in the South Pole region was relatively uniform in its composition, but it's only with Chandrayaan-3's on-the-ground measurements that scientists could confirm this. This is crucial for future lunar exploration, because it means that the data we collect from orbiting spacecraft can be trusted to accurately reflect the conditions on the ground. And that's not just important for understanding the moon. It's also essential for planning future missions. With renewed interest in returning humans to the moon, especially through NASA's Artemis program, having reliable data on the composition of the lunar surface will be critical for choosing safe landing sites and for planning the construction of lunar bases. But Chandrayaan-3's mission isn't just about science. It's also a testament to the growing capabilities of India's space program. ISRO has made significant strides in recent years, and Chandrayaan-3's success is a major milestone not just for India, but for the global scientific community. This mission has opened up new frontiers in our understanding of the moon, and it's laying the groundwork for future exploration. Speaking of the future, there's already talk of Chandrayaan-4. This next mission, still in the early planning stages, aims to bring samples from the moon's surface back to Earth. This would be the first time since the Soviet Union's Luna missions in the 1970s that material from the moon's surface has been returned to our planet. Such samples would allow scientists to conduct detailed laboratory analyses that are impossible with remote sensing or even on-site measurements. Bringing back samples would help resolve some of the questions raised by Chandrayaan-3's findings. For example, the presence of magnesium in the lunar soil at the South Pole doesn't quite fit with the existing models of the moon's crust. By studying these samples in detail, scientists could refine their models and gain a better understanding of the moon's geological history. In conclusion, Chandrayaan-3 has not only expanded our knowledge of the moon's South Pole, but also raised new questions about its ancient past. The idea that the moon was once covered by a global ocean of molten rock is becoming increasingly accepted, but the details of how that ocean cooled and solidified are still being worked out. With each new mission, we're getting closer to answering these fundamental questions about the history of our closest celestial neighbor. So, what do you think? Could the moon hold more secrets than we ever imagined? And how might Chandrayaan-3's discoveries shape the future of lunar exploration? Let us know your thoughts in the comments below, and don't forget to subscribe for more updates on the latest in space exploration.